So if you are exactly on the z-axis, if this is my center, and if this is my point P, which is at a height of z, then here the field will be just like this. It will be going just like this. And here also it will be the same. It will be going like this. And if you are if your observation point here is P at a height of z, then beneath also at a height of minus z, at this point P, it will be the same. So if I say this as P1 and this as P2, then they will be the same. Okay. And the last thing, that suppose instead of my observation point being, if my observation point being here, if my observation point is exactly here at the center of the loop. So if I see from here, then if this is my loop and if we are exactly at the center, what will be this value? This will again have only z component, but the value will be I over 2a. And how you can get this I over 2a? Very simple. You just substitute. Here z is equal to 0 because your now height is becoming 0. In our problem, we are looking at a height of z from the center. So make the 0 and you will get the answer. Okay. So this is for the ring. Now let's go to our next laws of magnetostatics. So in magnetostatics, we have, two laws, two fundamental laws. So first we have already seen the Biot-Savart laws. And as I have already told before, the Biot-Savart law is similar to Biot-Savart law is similar to the Coulomb's law in our electrostatics, and this is in the magnetostatics. Now you have two more laws. Now this is for your magnetostatic, that is static magnetic field. The first one is the Ampere's law, and the second one is the Gauss's law for the magnetic field. So you have the Gauss's law for the electric field. Remember, closed surface integral d bar dot ds bar is equal to the charge enclosed. So this is the Gauss's law of electric field. In the similar way, you will have Gauss's law of magnetic field that we will see later. And now we are looking at the Ampere's law. So what does Ampere's law states? Ampere's law states that the closed line integral of my magnetostatic field, along any closed line, okay, the line integral of my magnetostatic field along any closed line or along any closed path is equal to the current which is enclosed in that path. So this is in integral form. In differential form, you will get this. Just apply Stokes' theorem. So closed line integral h bar dot dl bar is equal to I, or del cross h bar is equal to j bar. So this is the Gauss's, the Ampere's law. So to visualize it further, so let me expand this. So to visualize this further, these are some of the examples. So it is saying that, see, if this is my small line and I'm fine, and this my H, this is my magnetic field H, and this magnetic field H is everywhere. And now if I integrate this magnetic field H over this closed line, it must be equal to the current which is enclosed. But here there is no current enclosed. That's why closed line integral over my closed path 2 is 0. Now, if you do it for 1, then it will be I1, I2. So it will be I1, I2. Why? Because they are going in different directions. So therefore it is I1 minus I2. Now, if you are doing it for the 3, then 2 currents are going up and 1 current is going down. So I1 plus I3 minus I2. So this is what the Ampere's law have stated. And of course, remember that why we gave I2 minus and why we gave I1 and I3 positive here, or why we gave I1 positive here and I2 negative here. It depends on your, the closed line integral, how you are integrating. So if you are integrating in the anti-clockwise direction, okay, if you are integrating in the anti-clockwise direction, then your, again, for this case, you can still apply your, right hand, and then your fingers will give you the direction in which you are doing the line integration of your magnetic field, and your thumb will show the current which will be the positive one. So here also it's the same thing. So if you put your fingers along this direction like this, then your thumb will show the current, because your fingers will be curving in this direction, which is the direction of your line integration. Okay, so keep this in mind. Now let's go and see how we can apply the Ampere's law. First, let's apply Ampere's law on an infinite straight line. So you have an infinite straight line, and this infinite straight line is carrying a current I. And what I'm doing is I'm now trying to find the magnetostatic field of this straight line. So what we need to do here, again, very similar to Gauss law, you have to first find the coordinate system. Second, you have to enclose your current in a closed loop. You have to enclose your current in a closed loop, and that, or a closed path. And this is a hypothetical path which doesn't exist, but we just put it to apply Ampere's law. So very similar to how we did it in the Gauss's law. We enclosed it in a closed surface, right? And then we applied Gauss's law to that closed surface, and that closed surface was a hypothetical one. So here also it's the same, but here instead of a surface you have a closed loop. So this is a closed hypothetical loop which I have drawn here, and this is called as Amperean path, closed path, or sometimes it is called as Amperean loop, Amperean closed path, or Amperean loop. So we have created this, and now we will apply the Ampere's law here. So this Amperean loop, as you can see, its radius is rho. So this is our rho radius. And now what I'm doing is I'm now finding a small elemental length of this Amperean loop here, because I need to do the closed line integration. So I'm defining this as dl, and this dl, because I'm using the cylindrical coordinates, so this small length will be rho d phi. It will be rho d phi, and since we have to identify the direction where we are going to move. So it is rho d phi a phi. So this is my dl. So I'm not just taking dl, I'm taking dl bar. Why? Because in the closed line integral, it is h bar dot dl bar. It's a vector. So you need to show in which direction you are moving. So therefore, it is just not just rho d phi, in rho d phi plus the direction. So direction means I'm moving in this direction. And what is this direction? This direction in cylindrical coordinates. Yes. Does anybody remember? Yes, Mr. Abdul Majid. Can you help me?
Yes, doctor.
Yes. So what will be the a phi direction? In
A phi.
coordinates? Yes. Do you remember? Phi. How phi is defined?
R phi, you say, or sorry, doctor, can you repeat it? It's not clear.
A phi. How is a phi defined? Or how is the phi plane defined in cylindrical coordinates? Do you remember?
By the angle, yes.
Yeah. So angle with respect to which axis?
XY axis.
With respect to x axis.
X axis, sorry.
Yeah.
But it is an XY plane, I mean.
Yeah. Yes. So yes, right. So this is your phi, and this direction is your unit vector.
A phi.
A phi. A phi. So that's why this is a phi. Okay. Thank you. Thank you very much, Abdul Majid. So once we do this, then let's apply the Gauss's law. Sorry, the Ampere's law. So that's why. So this is done. Okay. Now one more thing which I wanted to tell you. Remember, in Gauss's law, we need to know some little bit knowledge about how the electric field looks like, what will be its component that will be existing. So in a similar way for Ampere's law also, you need to know that. And we can easily find this by applying our right hand rule. Okay, so if I apply right hand rule by putting my thumb on along the current, then I know that my curving of my fingers will be in this direction. So from there, I can say that my magnetic field H will have only a phi component. And since it is curving, so therefore my H phi will only be, oh, sorry, just a second. It will have the H phi component. Okay, let's continue. Maybe I have to bring it down. Okay. So now let's go ahead and let's apply. So when we apply the Ampere's law, so closed line integral h bar dot dl bar is equal to the current enclosed. We got already this information. I'm applying the Ampere's law. So the closed line integral h bar dot dl bar. So I know h bar is h phi a phi. So my h bar is also in this direction, right? Because it is h phi a phi. And my dl bar is also in this direction, which is a phi. So you have a phi and a phi. Both are in the same direction. So therefore, the dot product of them will become 1. And that's why you can replace them with a simple multiplication. Is equal to the current enclosed. Which is the current enclosed here? This is my current. And what is the current value? I. So that's why I. Now, as you can see, in a very similar manner as we did it for our Gauss's law, so it is HDL. Now, H will go out, and you will get only DL here. And what is the line integration of this one, this circle, or this will be nothing but your circumference of your circle. And the circumference of the circle of radius rho is 2 pi rho. and therefore your H is equal to I over 2 pi rho, or H bar is equal to I over 2 pi rho times A. Okay, so this is how you can get the magnetostatic field due to an infinite line carrying current I. And again, see, this is the same result that we have obtained from the Biot-Savart law. Hence, again, we can say that the Ampere's law is the fundamental law, because from the Ampere's law, we are able to derive the Biot-Savart's law. So therefore, Ampere's law is the fundamental law and Biot-Savart's law is not the fundamental. Okay? Yes, any questions? Shall we move? Okay, so here we are doing it for a sheet. So if you see here, we are doing here for a sheet. So you have an infinite sheet. And this sheet is carrying a current. And the current is K bar is equal to Ky Ay. This is the sheet current, which is flowing here. It has only one component, Ky Ay. This is my current. Now, how do you apply the Ampere's law here? So you can apply Ampere's law by putting a small Amperean path here. And remember one thing, this sheet is placed in the XY plane. So this is placed at Z is equal to 0. So this side is Z is greater than 0. And this side is Z is less than 0. And if you want to see a side view, if you want to see from here, then it looks like this one, a straight line. And then you will have your Z axis, and this will be your X axis, and coming out of the screen will be your Y axis. And then what I am doing, I am now putting a hypothetical Amperean loop here. So I can put it anywhere. So according to this one, we have put it here. And then we are applying the Ampere's law. So this height is A, this is A, and this is B. Now, let's first analyze how the magnetic field will be for this sheet. Now, can we do the following? Can we think that this sheet is made up of several line charges? Can I say infinite number of line charges? Because this will help us to identify the magnetic field and its component, its direction. That's why. So you can think it in this manner, like this. So when I'm putting this dot, that means the current is coming out of the screen. Now, what will be the magnetic field for this one? So because they are made up of so many filaments, now the overall magnetic field will be added. So now can you add this? So what will be the magnetic field of this filament? It will be like this. This filament like this. This filament like this. Add like this, like this, like this. On this side, like this. See? So they will all add up. And the magnetic field which will be created will be something like this. And this is your sheet. Of course, if you go to the edges, then you will see this one. And if it is an infinite sheet, then the magnetic field will be like this. And in this direction, it will be like this. And this is our sheet. So remember, this is my sheet. And if I don't see the corners, and if I see the corners, then it will go like this. So this we can easily analyze by assuming that the sheet is made up of different infinite line charges and then adding all of them. Okay? So with this information, what we get is that our magnetic field is made up of only one component, which is X component. So in this region, which is Z greater than 0, and in this region, which is Z less than 0. So in this region, the magnetic field is going in this direction. So therefore, it is along the direction of X. So it will be AX. And let us say that its magnitude is somewhere H0, which is unknown. We will find it. And in this direction, that is for Z less than 0, it is H0 times minus AX. So this is our magnetic field. And therefore, this is just from our analysis, we found it. And now, if we apply the Ampere's law, closed line integral h bar dot dl bar is equal to the current enclosed. So what is the current enclosed in this loop? The current enclosed in this loop will be just this much of the current, right guys? See, only this much of the current. And what will be this current value? Yes, Ky, Ay. Yes, can anybody tell me?
Times B.
Time, you will not use Ky, sorry. It is Ky times B. And from where I am getting this Ky times B? It is from the definition of the surface current. If you remember the definition of the surface current, what was the definition of the surface current? The definition of the surface current that we used it. See, this is the one. Just take the component which is normal and multiplied by dl or integrate it over the dl. So this is exactly what we did here. We took the normal component of my current, which is only Ky, Ay is not required, and integrate this Ky over this complete length. And since your Ky is a constant, I can simply multiply by B. If it is a constant, otherwise I have to put the integral. So it is Ky times your integral over the L, your dl, and your dl should be this one. Okay, but since it's a constant, that's why we just got Ky times B, which is here. And now if I apply Ampere's law, then you will see that we have 4 line integrations. So if we do the 4 line integrations, then what you will see that you have 1 to 2, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. and I have decided the direction of the line integration to satisfy the right-hand rule, which I have just now told, that when the loop direction in which you are integrating, then your thumb should show the direction of the enclosed current. So since the direction of my enclosed current is in this direction, see, it is in this direction. So therefore, it has to be the anti-clockwise direction. Okay? And based on that, we do the integration. So this 1 to 2 and 3 to 4, they will cancel out, because here your DL is perpendicular to your current. So that's why these two will be gone. Now the only thing left is 2, 3 and 1. So if you do 2, 3 and if you do 4, 1, 2 to 3 and 4 to 1, then you will get this one. So 2 to 3. So in this direction for 2 to 3, so it will be integral 2 to 3 will be what it is. So 2 to 3, this is in the region Z is less than 0. So therefore, my H bar is minus H0 AX bar times DL. So what is my DL? What is my DL? What is my DL for this loop? I'm going from left to right and I'm doing the line integration. So this is which axis direction? The x-axis direction. And since it is x-axis direction, but we are going opposite. So that's why it is minus dx ax dot product. And then you will see that this is equal to 2 to 3 minus h naught, minus into minus plus h naught dx. So it will be h naught 2 to 3 dx. And what is your dx? Is this length, and this length is b. So it is h naught times b, which is here. H naught times b. Similarly, you can do it for 4 to 1. 4 to 1 is in this direction, right? So for 4 to 1, how you will get? Integral 4 to 1 is, I am now above z is equal to 0. So it is z is greater than 0. So that's why I will take this one. So h naught ax bar times my dx. Dx, what will be dl? Dl will be, again, it's a line integral along the x direction, but my line integral is along the direction of my x. So it is dx ax. So this will again give me h naught b, or in the end I will get 2h naught b. And what is this one? This is just now we got, it is kyb is h naught b. So what is my unknown h naught? Is nothing but ky is equal to, it is equal to half k. Just a second, I'll show you. So if you go down, so here you will see that kyb, which is my this one, is equal to 2 h naught of b, h naught of b plus h naught of b. So b cancels, my h naught is ky over 2. And therefore, I'm just substituting it back. So this is the magnetic field of an infinite sheet, AX. And if you want to generalize it, it is nothing but it is equal to half times my current vector cross a unit normal vector AN. And this unit normal vector is directed from the center, from the current sheet to the point of interest. So if my sheet is here and my point is here, so what will be AN? AN will be It is the unit vector directed from the current sheet to the point of interest. So from here to your point of interest. So which will be this. This will be your A. This will be your A. Okay. So whatever we got, we are just putting it in a vector form. So any questions, guys? Just go and just, I suggest you, just apply the same generalized expression for our case, for the case that we have just not did. Just apply the same for this case and check whether you are getting back this or not. And you will get back this. So you can just do this as a practice in your home and you will get this answer. So therefore, we are using a generalized one because your sheet can be in any plane, XY or YZ or XZ, any plane. Okay. Now, this is one more example. And I think with this example, we will stop. So this is the example of, again, a wire, but this wire is of non-negligible thickness. If you see here, so it's a wire, long wire, but it's of non-negligible thickness. So it has a cross section and it's an infinite wire. So the length is tending to infinity, but the wire has a radius A. And now it is placed on Z axis. Now we need to find what is the magnetic field which is generated by this wire. So again, we will do the same. What? We will apply the Gauss, the Ampere's law. So first, let's apply the Ampere's law. So here, if I see the top view from here, then this is my wire. Okay. Now I need to find the magnetic field which can exist inside or which can exist outside. So let me first see what will happen if we are outside. So I'm putting an Amperean loop and then I'm trying to find the Ampere's law. So this has a radius of rho. So see here, the closed line integral h bar dot dl bar is I enclosed. So the closed line integral h bar dot dl bar is equal to, what is the current enclosed here? Yes, inside this loop, what is the current enclosed? Yes, Mohammed Albush, can you tell me what is the current enclosed in this loop? Yes, Mr. Mohammed Albush, are you there or no? No? Yes, Zuhair, you can tell me.
Isn't the current enclosed parallel to the z-axis or
Yes.
parallel to the vertical axis?
It is the total current enclosed because your current is flowing in this direction, guys. And this current is here, it is completely here. And my Amperean loop is this one. So the current which is enclosed in the Amperean loop is the whole current I. That's why it is I here. Okay. I think it's time, guys. Maybe we will just take this in our next class. And then we will go to the solenoid and the toroid. Okay. So before stopping, anything else you want to ask? Okay, then. So we will meet on Sunday and we will have our quiz on Sunday. Okay, thank you.
Thank you, Doctor. The homework will be postponed.
Yeah, I will send an email.
Thank you.